Good morning, class. I hope you're having a great day. I have uploaded an additional practice problem, and we are going to use the law of conservation of energy to help us solve this problem. So I'm going to read the problem to you. We're going to generate a column of knowns and unknowns. We're going to draw a simple picture, and then I'm going to help you with the 4 parts to the problem. So let's go ahead and get started. A 35 kilogram rock is on the edge of a 105 meter cliff. So what let's go ahead and do right now is just draw a simple picture. So we have our reference level, and remember that our reference level is when the height is equal to 0. It also tells us in our notes that the reference level represents the position where the potential energy is equal to 0 joules. So here we have our rock. The height of our rock is 105 meters with respect to our reference level, and the mass of the rock is 35 kilograms. Okay, in part A, it wants us to calculate the gravitational potential energy relative to the base of the cliff. So we're going to use PE, the gravitational potential energy for an object, is equal to mass multiplied by the acceleration due to gravity multiplied by the height above the reference level. So what we have is 35 kilograms times 9.8 meters per second squared multiplied by the height, which is 105 meters. So let's go ahead and get out our calculators. We'll do the calculation together. So let's just take the product of these 3 values here. 35 times 9.8 times 105. This is going to give me 36,015. Okay, so let's take a look at our units here. I have kilograms over 1 times meters per second squared times meters over 1. Okay, so what we have is kilogram meters squared per second squared. Now what we want to do here is factor out one of our meters, which is going to give me a kilogram meter per second squared times meter, which is meters over 1. And you know that a kilogram meter per second squared is equal to a newton. So what we have here is a newton meter. And whenever we're describing gravitational potential energy, a newton meter is a joule. So our answer is 36,015 joules. Right here, so part A, 36,015 joules. Okay, let's take a look at part B. So part B wants us to calculate the kinetic energy as the rock hits the ground. So what we're going to be doing is using the law of conservation of energy. And it tells us in a closed and isolated system, the energy cannot be created or destroyed. The energy just changes form. So what we have is our mechanical energy, our initial mechanical energy in our system will equal the final kinetic energy. Now we can expand this. We know that mechanical energy is the sum of the object's kinetic energy and the gravitational potential energy. So what I have is the initial kinetic energy plus the initial gravitational potential energy is equal to the final kinetic energy plus the final gravitational potential energy. Now we can go ahead and expand this further here. So we know that kinetic energy is equal to 1/2 times the mass times the velocity squared. but this is our initial, so we need to say initial velocity squared. Initial gravitational potential energy, so this is mass times gravity times the initial height with respect to our reference level. This is going to equal the final kinetic energy, 1/2 times the mass, multiplied by the final velocity squared, plus our final gravitational potential energy, so mass times height times, mass times gravity times height. I want to be consistent, so sorry about that. And this is our final height. Okay, now before we start plugging in values here, let's go ahead and make it easier on ourselves, and we can eliminate some of our variables here. So the first thing I want to talk about is the initial kinetic energy of our rock. So right up here, the initial velocity is 0. So when our initial velocity is 0, 0 squared, it's going to be 0. 0 times mass in 1/2. We can get rid of all of this because it goes to 0. So we don't even need to worry about it. Now, we know that the rock, its final position is at the reference level. The rock hits the ground. So when it hits the reference level, its gravitational potential energy is 0 joules. So let's go over here. The final height, this is 0. So all of this goes to 0. Okay? So what I'm left with is the initial gravitational potential energy of our rock is going to be equal to the final kinetic energy of our rock. And the question is asking, what is the final kinetic energy as it hits the ground? Well, so we have mgh, and this is our initial, and we have actually already calculated this. So we know that the final kinetic energy is going to be equal to the initial gravitational potential energy, so 36,015 joules. And I'm just going to write that up here. And remember, we're using the law of conservation of energy, where, remember, it's telling us that the energy can only change forms. It cannot be created or destroyed. Okay? Part C. At what velocity does the rock strike the ground? So what we're going to do is use the equation for kinetic energy. We know that our final kinetic energy is equal to 1/2 times the mass times the final velocity squared. Okay? Now we know the final kinetic energy of our rock, and we know the mass. So what I want to do is isolate final velocity squared by dividing by 1/2 and mass on both sides of the equal sign. On the right hand side, the mass and the 1/2 will both cancel. So I have final velocity squared is equal to my final kinetic energy, which is 36,015 joules. And let's go ahead and break up a joule. Remember that a joule is a Newton meter. And we know a Newton is a kilogram meter per second squared. And we're multiplying this by a meter. And algebraically, we can write that as meter over 1. So what I'm going to have here is kilogram meter squared per second squared. All right. In our denominator, we have 1/2. Our mass is 35 kilograms. Okay, so what I want to do now is just resolve the denominator. So I've got 36,015 kilogram meters squared per second squared. And 1/2 times 35, that's 17.5 kilograms. Okay? So what I want to do first is look at the numerical value. So on our calculator, let's divide 36,015 by 17.5. And this is going to give us 2058. Okay? So let's take a look at our unit value right now. So I'm going to erase to free up some room here. So we have kilogram meters squared per second squared divided by kilograms, and we can say kilograms over 1. Remember, whenever we divide fractions, it's like multiplying by the inverse of the denominator. So I have kilogram meters squared per second squared times the inverse of the denominator, which is 1 over kilogram. Units of kilograms are going to cancel. So my units here are meters squared per second squared. But you might say to yourself, well, those units look funny. Well, that's correct, because let's take a look at the left-hand side of the equal sign. We have final velocity squared. So what we have to do is get rid of this squared. So we're going to take the square root of both sides of the equal sign. I'm going to erase here. So let's get out our calculator. Now remember, when we're taking the square root of this, not only are we taking the square root of the numerical value, we're also taking the square root of the unit value. So 2058, let's take the square root of that guy. This is 45.365. Here, I'll just say 45.37, okay? And we're going to take the square root of meters squared per second squared, which is going to be meters per second. Now remember that velocity is a vector, and we know that the rock is falling in a negative y direction, so our vector is not only going to show magnitude but direction. So we can say down negative y direction, we can draw a vector arrow if you want, or you can simply use a negative sign. So part C, at what velocity does it strike the ground? Final velocity is a negative 45.37 meters per second. Okay, let's take a look at part D. Part D, it says check your answer for the final velocity. Okay, what we can do is use the equation. The final velocity squared is equal to the initial velocity squared plus 2 multiplied by the acceleration due to gravity multiplied by the final displacement of our object. And we know right up here the initial velocity of the rock is 0 meters per second. So 0 squared, we can go ahead and get rid of this guy. This goes to 0. So final velocity squared equals 2 times negative 9.8 meters per second squared multiplied by the displacement. And remember, displacement is a vector. So this rock falls down, so it falls in a negative y direction, 105 meters. So negative 105 meters. Okay, so negative 9.8 times 2 is going to be negative 19.6 meters per second squared times negative 105 meters. So let's go ahead and take the product of these two values, and then we'll talk about the units. So we get 2058, and this is going to be positive here because we have a negative times a negative. So 2058. I have meters per second squared times a meter. So meters per second squared times a meter. And we can write that as meter over 1. So you'll see that our units are going to be meters squared per second squared. And we have, once again, a square on the left-hand side of the equal sign. So what I'm going to do is square root both sides. On the left side of the equal sign, when we take the square root of a value that's squared, that exponent will cancel out. So let's take the square root of 2058, and I get final velocity equals 45.37. The square root of meters squared per second squared is going to be meters per second. And remember that velocity is a vector and it's going down, so we checked our answer using another kinematics equation, and so we know we completed the problem correctly. So if you need any help, please send me an email. I hope you have a great day.